Continuing on in section 3.5 here, we're going to solve this system of equations using substitution. Okay, we're going to use substitution to solve this system of equations. If we look here, I have x, y, and z in my first equation, x and y, no z in my second, and z and x in my third, no y. So elimination here isn't going to work. We're going to use substitution instead. And in order to do that, I need to rewrite one of my equations for a variable. So I'm going to solve for x here because I don't have to divide by anything. My coefficient's a 1. I'm going to subtract a 5y. So x equals 9 minus 5y. Now that I know what x equals, I substitute that into my other two equations. Okay, has to be into the other equations, not into the original one that we solved here for x. So I have 2 times x. X here is 9 minus 5y plus 3y minus 2z equals negative 1. And my second equation, I have 4z minus 5x. And remember that x is going to be 9 minus 5y. And that equals 4. I'm going to simplify my equations here. I'm going to distribute. Combine my like terms. And then get it in standard form, which means alphabetical order with variables on one side, number parts on the other. Same idea here. When I distribute, though, don't forget to take the negative with our 5. So 4z minus 45 plus 25y equals 4. Again, I'm going to get it in standard form. So 25y plus 4z, add 45, gives me 49. Now, I have two equations with two variables, y's and z's. So I can put those together and form a system. 25y plus 4z equals 49. So once we get to this step right here with our two separate equations with two variables, we solve the same as we did with elimination. So here we can either use substitution or elimination. I'm going to use elimination. I don't have opposites, but I can get some by multiplying the top by 2. And putting those two together. I have opposites. I can go ahead and add 11y equals 11, divide, and y equals 1. Now that I know y, I can substitute it in for y in another equation that just has one variable in addition to the y. Subtract to get my z term by itself, and divide. I have y and z here. I can find x. I know that y is 1. So I substitute in a 1 there. X equals 9 minus 5, which is 4. So I have 4, 1, 6. So again, once we get here with substitution, it's the same as it was with elimination. We put our two equations together into a system and solve. I'm going to solve here using substitution as well. We could use elimination fairly easily here, but I'm going to use substitution just to get some more practice on that. If we look here, we have a few options as far as the variable to solve for. It looks like we could solve for x or z in the top, y in the middle, or z in the bottom. I'm going to solve for x just because it's the first variable I see that looks easy to solve for. And I do that by adding 2y to both sides and subtracting z. So I get x equals negative 4 plus 2y minus z. Now that I know what x equals, I substitute that in again to my other equations for x. So I have negative 4 times x and I bring the rest of my equation down. Plus y minus 2z equals 1. And I have 2 times x, but again, we know x here is going to be negative 4 plus 2y minus z plus 2y minus z equals 10. I'm going to distribute and simplify here. Try and get it into standard form. So my first step is distributing. Then I'm going to combine like terms. And get it set equal to my constant. I have it in standard form. Same idea here. I'm going to distribute all the way through. Combine my like terms. And get it set equal to my constant. So I move my constant to the other side. Now, I have two equations that only have two variables in them. I can put these together. And again, once I get to this step here, I solve it the same way as I did with elimination. I combine them into a system of two equations and two variables, and I solve. I don't have opposites here, but I can get some. I'm going to multiply the top by 3, bottom by 2 to get rid of my y's. I could have done it with the 7 and the 6. I just prefer to use smaller numbers. Keep my numbers a little bit more user-friendly. So I get negative 21y plus 6z equals negative 45, and 12y minus 6z equals 36. Now that I have opposites, I can go ahead and add. Negative 9y equals negative 9. Divide, and I get y equals 1. Once I know what one variable is, I can work backwards to find the others. So I know y is 1 here. So I get 6 minus 3z equals 18. Subtract 6 and divide, and z is going to be negative 4. I know what my values are here for y, which is 1, and z is negative 4. Minus a negative gives me a plus. So x equals negative 4 plus 2 times 1 plus 4, so x is going to be 2. We write our ordered pair again, x, y, z, 2, 1, negative 4. And that is my solution. Again, we can check that by plugging in to every equation and making sure all of them give us true statements. Here we're going to solve a real-world problem. You manage a clothing store and budget $6,000 to restock 200 shirts. You can buy t-shirts for $12 each, polo shirts for $24 each, and rugby shirts for $36 each. We want to have twice as many rugby shirts as polo shirts. How many of each type of shirt can you buy? So we have 3 different variables here, 3 different things that we can change. We can have t-shirts, polos, and rugby shirts. Those are our 3 types of shirts. So I'm going to make this T, I'm going to make this P, and this R. We also have 2 totals that we're talking about, a total of $6,000. So one of them is going to deal with money, and a total of 200 shirts. One's going to deal with quantity. And then our third relationship is in this sentence. So as far as our budget goes, those are all of our prices. T-shirts are $12 each. So we take 12 times the number of t-shirts. And polos are $24 each. So 24 times the number of polos. And rugby shirts are $36 each. So 36 times the number of rugby gives me $6,000. So price times quantity gives us cost. And if we add up all 3 costs, that gives us the total amount that we can spend, $6,000. The quantity here of just having 200 shirts just means we're going to add up all the types of shirts. T-shirts and polos and rugby shirts equal 200. Keep in mind, we need at least as many equations as we have variables. Here I have 3 variables, so I need 3 equations. And the third one comes from the starred sentence here. We want to have twice as many rugby shirts as polo shirts. So we have to ask ourselves, which one do we want more of between rugby and polo? Well, we want twice as many rugby shirts as polo shirts. So rugby is going to be more. Rugby is going to be twice as many as polo. So 2p equals r because we want more rugby, so I take polo times 2. Now, I have a system of equations here. I know what r is, so I'm going to substitute in for r here in my other two equations. I'm going to get 12t plus 24p plus 36 times 2p equals 6,000. It's going to give me 72p when I multiply. So 12t plus 96p equals 6,000. Same thing here. I'm going to take that 2p and plug it in. So I'm going to have t plus 3p equals 200. Sorry. Now I have a system here. I can solve it by either substitution or elimination, doesn't matter. I'm going to multiply all of them by -12 just because I'm kind of partial to elimination. If you prefer substitution, we very easily could have subtracted the 3p here and solved for t. So I'm going to get 12t plus 96p equals 6,000 minus 12t minus 36p equals -2,400. Now I have opposites, so I can go ahead and solve. I get 60p equals 3,600. P is being multiplied. I can go ahead and divide. And polos are going to be 60. Now that I know polos, I can find rugby. 2 times 60. I get 120 rugby. 60 polo. And I can find my t-shirts here by substituting back into one of my original equations. So I'm going to have t plus, we said polos were 60, plus rugbies we said were 120, equals 200. So t plus 180 equals 200. Subtract, and t-shirts are going to be 20. Okay, so again, we have 20, 60, 120 for our values here. And it all comes down to how we set up these equations. We had two different totals. One was talking total price, total amount we're going to spend. And when we spend money, it's quantity times cost, or how much the price is. Price times quantity. So the total amount spent for t-shirts is 12 times the number of t-shirts we buy. The total amount spent for polos is $24 each, so times the number of polos we buy. And the total amount spent on rugbies is 36 each, which means 36 times the number of rugbies we bought. And we add all those up, and it should equal 6,000. The second one was just quantity, just how many shirts. So we take just how many t-shirts we have, and how many polos, and how many rugby shirts. Set it equal to 200. And then the last one, we want to have twice as many rugby shirts as polos. So stop and think there. What does that mean? Which one do we want more of? Well, we want to have twice as many rugby as polo means we want more rugby than polo. So the 2 for the twice is 2p equals r. We can substitute, put our system together, and either use substitution or elimination once we get to this point to solve. Quick recap here. Systems of 3 equations and 3 variables can be solved using some of the same algebraic methods used to solve systems of 2 equations and 2 variables. If the equations of 2 systems are equivalent, then a solution of the system that is easier to solve is also a solution of the more difficult system. And that's all I have for section 3.5.